this computer. Recording progress. Okay. 6:05, let's get started. So I'm Alvin. I am one of the workshop leads this term. From the Data Science Club, I'm in second year mechatronics, which is not in fact stats or math or data science related, but I'm in the Data Science Club, so that's cool. That's Anthony.
I'm Anthony. I'm in econ, which is also not really in math, but well, I'm in joint honors, so kind of in math, but not really. So yeah, that's me. I'm fourth year as well.
Yeah. I think if you were here during the NLP workshop or reading group, you have seen me before. I think that's all the workshops / reading groups I'm gonna do this term. There's a bunch of other people doing workshops the rest of the term, and it's gonna be fun. Today we're gonna talk about computer vision, and computer vision is actually a very, very broad field where it's like anything that deals with the computer learning how to see, how to perceive the world. So the very, very common kind would be computer vision, where we're looking at images. But of course, there could be also other things, other sensors. So it could be something like LiDAR, for example. If you were in the reading group yesterday, I presented a LiDAR paper, or like radar and stuff like that. So, and there are a lot of different tasks in computer vision. So usually the most common one would be classification. So you feed in an image and then it outputs something like 0 and 1s, and then you process that data into classes and then classify images into like cats and dogs or something like that. There's also like segmentation stuff or object detection where you draw boxes around specific areas of the image. But for intro purposes, this workshop will only cover classification because that's the easiest thing to explain. And object detection is not an easy thing to explain, as some of you may have noticed yesterday. So yeah, overview. It's very introductory compared to the NLP workshops because some of you complained about the NLP workshop being too difficult. So we're actually going to start with like what neural networks are and like what are layers and what are the different types of layers that make up a neural network, and then we'll move on to CNNs, convolutional neural networks, which are the networks that usually computer vision practitioners use to process camera images or even LiDAR stuff. So yeah, Anthony and Joel.
All right. So for those of you who are kind of newer to machine learning, it can kind of be broken down into these three categories that you see here. There's supervised learning, there's unsupervised, and there's reinforcement learning. If I can give you one piece of advice, try to learn about supervised learning first, because reinforcement learning is a whole new world and unsupervised is also kind of a whole new world. Supervised learning is when you provide actual labels and you say to you take a statistical model and you teach it things about data that you've already provided to it with answers. So generally you're saying like, this house is worth this much money and it has 4 bedrooms, for example. You provide the data and the model will learn about the correlations between the inputs and the outputs. Unsupervised learning, on the other hand, deals with data that doesn't have labels. So housing data that like wouldn't have a price would be unsupervised if it tried to learn ways to estimate the housing price without the answer given to it. And then reinforcement learning is it performs a task. So a model will perform a task and it will improve by, there's a reward function, and it improves by slowly maximizing that reward function by doing that task over and over and over again. And usually this takes a lot of time, a lot of data, and it's generally it's kind of like its own. So that brings us to supervised learning, which is kind of when people talk about machine learning, usually they kind of refer to supervised learning. That's like the basic level. So there's classification and there's regression. Classification means predicting like one of n labels. So in this case, for our demo, you'll see later on, we're going to be performing classification on pictures of dogs, and we're going to be classifying the breed into one of 70 categories. So there's 70 types of dog pictures, and we're going to be predicting what kind of dog it is based on the picture. And then on the other hand, regression is predicting a quantity, like a real value. You can think of it as that. So the housing price is a common example, as I mentioned previously. And then there's also all sorts of other regression problems, such as like maybe you want to predict a stock price, or really anything that isn't a label, right? When you have just a value, a real value you're trying to predict. Next slide, please. So that brings us to neural networks. So this is a standard vanilla neural network. We have an input layer, a hidden layer, and an output layer. This is about as simple as it gets, but a lot of commonly used neural networks get a lot more complicated than that. They may have a lot more hidden layers, and there's a lot more work that goes into them. So the neurons are the circles that connect this. You can think of it as a graph, and the neurons are the circles that connect to each of the other layers. So you'll notice that each circle in the input layer connects to each layer, each neuron in the hidden layer, and then each hidden layer neuron connects to the output layer as well. So it can receive one or multiple inputs, and the output of each circle, each neuron, is calculated. It's calculated with an activation function, it's called, and we'll talk about that in a second. So generally, the input layer is what you're feeding into the model, really straightforward there. The hidden layer refers to all the work done in between the computations that are going on behind the scenes, kind of. You can think about it like that. Traditionally, it's been seen as kind of a black box, but recent research is showing that it may not be as black boxy as we think. Spoilers for one of the papers that are going to be read soon, I think, for the paper group. I don't know. Is it? I don't know. Albert, actually, do you know that?
Yeah, I heard about that paper.
Okay. It's not being read, though, is it? That should be read in the
I don't know.
Anyways, lastly, we have the output layer. So in a classification task, you may have, like, if you have like 70 dog breeds, for example, you may want to have 70 neurons that output what the prediction for that class is. So how strongly it thinks that class, that it should be, like, for example, a Yorkie dog breed, for example. And that's the final layer of the neural network. So what goes on, the work in between the neural network that I was talking about, it's pretty much, if you've ever seen, y equals mx plus b, it's that, but it's with a lot more. So you have like all these layers, and then you have a bias term. And this is really like, it's a sum, but it's usually seen as a vector. But it's basically, you have the input x1 times the weight, which is it's what's it called? It's like a labeled connection. If you're familiar with graphs, it's like a labeled edge. And it goes to the next layer, and then it's the linear combination of those plus some bias term. And that's the work that goes on in between there, in between the layers. And this happens for all the layers eventually until the last layer comes out. And what happens in between all of these is we have an activation function over there. The idea here being that we may want the values to be within a certain range. You may want them to be non-negative, which is there's a commonly used activation function called a rectified linear unit that endeavors to make it a continuous non-zero function, or non-negative function, sorry. And then once you have that activation, we provide the output with that.
You're kind of muffled sometimes.
I am?
Yeah.
Oh, that's weird. Sorry, I have no idea.
But yeah, when people say they're training a model, which terms are they training?
Pardon? Sorry, I was fixing my mic.
When people are training models, what terms are they training?
So the parameters that we're training with the model are actually these weights and biases. They get updated as you feed in the neural network data. It'll compute. You basically feed in the data to the neural network, and it computes how wrong it was, and it nudges all of these weights and biases. So these M, there's WM there. It goes W1, W2, W3, WM. All of those weights get nudged in a certain direction that makes it less wrong based on the examples that it's seen. And the bias also gets nudged up or down depending on what each of the examples needs. So in code, we have This is using the Keras API, which if you're getting into neural networks, I recommend. I think it's fairly intuitive. But some people would disagree with me. But I think it's pretty good. So you start by declaring or creating a sequential object, and you can add layers into it. So in this case, we're adding an input layer with 16 inputs. And then we're adding a dense layer, and dense just means it's fully connected to the previous layer. So you add the dense layer with 16 connections. So each of the 16, if you imagine that picture that we just saw, there was before there was like 4 blue dots. In this case, there'd be 16 blue dots, and then there'd be 32 dots in the middle. And then on the output layer, you have the dense layer with 32. And then the output shape will have 32. There'll be 32 entries in the output shape, as you see there. That's what's being printed with model.output shape.
How do you choose these hidden layer sizes?
That's a great question. Thank you for that. So I think the honest answer is that it depends. It kind of depends on the problem. Like you can play with them a lot. That's oftentimes when there's improvements in machine learning, they've been from just, or maybe not improvements in machine learning papers, but there's a lot of opportunity for improvement with playing with different architectures. So you can try. I think the answer to your question would be just plug and play. But if you know something that I don't, feel free to add on to that.
Yeah, I guess usually the higher the number, the more complex stuff it can encode. But when you have too much, then it doesn't usually, it's not always the case. And I guess if you're reading like machine learning papers, these numbers are always in the powers of 2, 16, 32. There's no like solid reason for that except that it looks nice. But yeah,
That's true.
hidden layers.
So loss and optimizers. So we have, like I said before, do you remember how I said we're nudging each of those weights and then the bias term for each layer? Each layer has its own bias term, by the way. It's so each layer has its own parameters that we're updating. And the loss function, we have a loss function that basically tries to tell the model how wrong it was, and that's what ends up being used to improve upon the parameters that may have given an incorrect answer on a training example. So it basically just calculates the error, and we'll go into examples. And then optimizers take that loss, and optimizers are what update those weights and biases. They give the instructions to update the weights and biases. You can think about it like that. So this is an example of a loss function that is used for regression problems. It's called mean squared error. Basically, you just take the difference between what the model predicted and what the actual value is. You square it and you add it up, and then you do that for each of the classes, and then or sorry, not the classes, each of the training examples, and then you take the average of them. So that's why the mean squared error, right? Now this is good for regression. It's a commonly used one for regression, but it's not very good for classification. The kind of intuition about that is that you want the loss function to be differentiable, and if you're predicting 1s and 0s and the answers are 1s and 0s, it's not really it's going to just be a bunch of dots of 1s and 0s that the errors are at. So it's not really used. It's not really used for regression, basically. So we'll talk about a loss function that is used for classification. Sorry, this is used for regression, not classification. And now we're going to talk about what is used for classification.
Oh, someone in the chat asked why we square it before we take the mean of.
That's a great point. So imagine that a house is worth $100,000. If you don't square it, and the model predicts either $200,000 or $0, the error would basically add up to be 0 in those cases. You want to penalize it in both directions if it's wrong in the negative direction or in the positive direction. So to do that, we square away the term. Does that give you some intuition about that? I didn't actually see that question, huh? Anywho, so in terms of loss functions for classification, this is a continuous and differentiable function that is used to compute how wrong a model that predicts classes was. So y is 0 or 1, that's the value So I'll stop with the dogs thing, because we'll get to that. But imagine we're predicting, one of the most classic examples is a Titanic data set. 1 is someone survives and 0, someone dies. So Y would be this kind of communicating if the person died or not. And then Y hat is the predicted value. And then we calculate it as follows. If it's true, then we have Y times log of Y hat. And a bad prediction will have a big negative with log of Y hat, and a good prediction will have log of Y hat go to 0. And then if true is actually 0, so if the person died in the Titanic, then 1 minus Y times log of Y hat. And then a bad prediction will have a big negative, and a good prediction will have a 0. I like the big negative description.
Yeah. So
Big negative.
like in both cases, the bad prediction would have a big negative, which pushes the model forward. And if it has good prediction, then the weight is good. So you don't have to push it any further. So the loss is less.
So then we talk about optimizers, right? So gradient descent is the typically used optimizing algorithm. If you've ever taken Stat 341, they won't let you leave that course without learning about Newton-Raphson. That's another optimization method that is actually available in some Python libraries. But gradient descent is typically is like the most widely used and accepted, because there are ways to do it that are computationally nice. So generally, if you see all those blue dots, do you see all those arrows, right? Those arrows are the model predicting better, basically. It's getting closer and closer to the real value. So what it does, gradient descent, is at each point of this, it calculates the gradient at that point, which is just like the slope of the tangent line. And it uses that information to nudge all the weights and biases up, and then it slowly improves upon its prediction until it approaches the true value there. You can see that in this 3-dimensional graph on the right, it's kind of like, so the one on the left is 2-dimensional, right? This is 3 dimensions when we have more features and stuff. And we're getting to the bottom there because we're minimizing the cost function on a batch of training examples, for example. So yeah, I think that covers optimizers.
So,
If you're interested, Stat 341 is pretty good. Yeah. So we'll get into some terminology. So batch size refers to the number of training examples before the training parameters are updated. And then epoch is the number of cycles through the training data. So fit and train is the process, like when you say you're training a model, it's the process of changing the weights and biases by calculating the loss function and then using an optimizer to improve upon the parameters and create better predictions. The learning rate is a scalar multiple that kind of limits how much the optimizer will learn in one step. This is really good. This is really important because if you don't limit it, it can just go off into infinity if the batch size isn't big enough. For example, if you have no regularization here. Class, it just refers to a label, and backpropagation is an algorithm that calculates the gradient efficiently, and with gradient descent, as we previously mentioned. So it's really just think of it as a way to calculate the gradient.
so there's 3 values like mentioned here. So there's batch size. How do we choose batch size?
How much compute do you have? That's kind of the answer. You don't want it too big. Basically, if you had a batch size that was just the whole training data, your model would probably never finish training, depending on what you're doing. Maybe if you have like a linear regression, it would be fine. It doesn't really make sense to do linear regression with gradient descent anyways. But anyways, yeah. So batch size, honestly, the answer for batch size is sometimes you just need to look at other people's code and see what they were able to do on a similar machine. Because when you're training really big neural networks, you're likely using something called the GPU. And in order to actually get that done, done in like a timely manner specifically, you need to maximize what your GPU can do without running out of VRAM. So that's pretty much the answer for that. I assume you're going to ask about epochs next.
Oh, I'm just gonna add to batch size. Usually in
Oh, sure.
a lot of like natural language processing papers, natural language processing not mentioned in this slide at all. Usually the larger the batch size, the better the model performs. And even though they're limited by sometimes the machine's virtual memory, they use something called gradient accumulation to pretend that there's more in the batch before doing back propagation and updating the model. So yeah, usually the larger it is, the better, but really depends on your data and what type of models you're working with. So epics.
Epics. Yeah.
Yeah,
Um,
I guess for epics, the more you have, the better the model performs. But what's stopping me from training a model for like 10,000 epics?
Time. Your lifespan. Your lifespan is stopping you.
Yeah, but let's say I have a lot of time and a lot of GPUs. Why can't I just train it forever?
Eventually you'll overfit to the data basically. The more like, because adding epochs is great, but you're still working with the same data set, so eventually it'll start just memorizing the data set perfectly, and then you won't actually be gaining any out of distribution improvements. So when you go to a new data set, the model won't have gotten any better, even though you spent 10,000 hours more.
Yeah. So he mentioned the word overfitting. That's when the training data, the model basically memorizes the training data, and then the test data, which is the data that the model has never seen before, starts becoming worse because it just memorized the data without actually processing it properly. Uh, yeah, let's go to CNNs. Uh, a couple of questions first. Why don't we just use ANNs for convolutional neural networks? Well, when you think about an image, the data type of an image is width by height by the number of channels. So channel means something like RGB. So that's 3 channels for image. And that's for a still image. This is a GIF, so it doesn't count. So we're looking at 3-dimensional data. Even though the image is 2D, there's still like an RGB axis. And when you think of the normal image, there's probably like tens of thousands, hundreds of thousands of pixels in there, and that's not very, very efficient to train on a artificial neural network because having that many input nodes is not very great for your network, and it's not great for a machine either. And these pixels are not properly processed within its spatial context. So like these pixels are just individually fed into the neural network. So the model is not really learning anything new, and it's very hard to train. So people use this thing called convolutional neural networks to train images, basically. And I will talk about um, some of the building blocks within a convolutional neural network and go on from there. So I'm gonna go with like a few goes. So the first go would be the simplest, and the fourth go would be the hardest. Um, Convolutional layers. So a CNN is made of like convolutional layers, pooling layers, and fully connected layers. Convolutional layers are the layers that extract features. This is usually what you see when you search up like CNN, other than the news organization CNN. The convolutional layers are these things in between, and they are basically feature extractors. That's basically what they do. For pooling layers, they are there because even after feature extraction, you're still dealing with a lot of data. The pooling layer is basically there to reduce spatial dimension, so the model doesn't have to suffer that much. And in a lot of cases, after you extract features, you don't actually need like every pixel of that feature. You can just pull it, like basically take the mean of some pixels around a certain pixel, and then basically reduce the size of the image before throwing it into the next layer. And fully connected layers would be something like a dense layer, or like one of the ANNs that Anthony mentioned at the very beginning. So towards the end here, you would see the classification layer where it's just a bunch of different nodes leading to the output layer where the classes are defined. And as I mentioned before, um, we're feeding in 3D data, so width, length, and channels, 3 different channels. But for CNNs, as you go deeper into the network, you actually have more and more channels. And those don't really mean RGB anymore. For a CNN, the increase of channels mean that the model is extracting more features. And as you go towards the fully connected layer, you are extracting larger and larger features. So at the very, very beginning, you would extract features like a dot or like a certain edge within the image. But towards the second layer, you might see like eyes or like a sleeve or something like that. And then towards the end, you would see something like wheels or like whole hoodies or clothes or hats. And basically, the deeper you get into a CNN, the more pixels you look at the same time. And the next go will explain why. Um, as I said before, convolutional layers are here to extract features. They are feature extractors, and they are there to extract edges and something like that. And we use something called filters that go over the entire image to do that. And I'll talk about filters more in the next slide. It's just a vocabulary that I'm throwing at you for the moment. And pooling layers, they're here to summarize things. And there's mainly two different pooling layers that people use. One is mean, the other one is max pool. On the bottom right here, we have basically a demonstration of a max pooling operation. So imagine this as a 2D image. We have how many 16 pixels here, and we want to reduce that to 4 pixels. So we pull these four pixels together and take the max value out of these 4 pixels. So 2249, the max pixel would be 9. You throw that there. 361, the largest one is 7, so throw it over there. That's the max pooling operation, and it kind of it still preserves a good amount of pixel information without losing a lot, while also making the model lighter so that it doesn't have to process every single pixel out there. Fully connected layers, it's the output layer. We already talked about it. Third go. We're back to convolutional layers. They are feature extractors. And we have something called filters that move across the image to extract features. So what are these filters? The filters would be something like the yellow square that's moving around. The black numbers are not the filter values. The red values are the filter values. Basically, you are doing a convolution, and I'm not sure if any of you guys, because you guys are in first year, so you shouldn't have encountered convolutions before, but you're basically multiplying these values together and then throwing the sum of that output into a feature, and that's a convolved feature. And these are actually these came way before convolutional layer CNNs are involved or like invented. Filters has always been a thing, and before CNNs were like introduced, filters were manually crafted to extract like edges using like Sobel filters or something like that that you might learn in like a very intro image processing course. But yeah, these values basically in a neural network, these red values are trained to extract useful features out of out of an image. And then we have more vocabulary. Kernel is basically like one dimension of the filter. Filter is just multiple kernels stacked together. Convolve, the process of convolving is just what this yellow thing is doing. It's just looping over the entire image. And stride is how much this yellow square moves. So in this GIF, a stride of 1 is used because it's moving one square at a time. But for some larger images, you might see filters strides of like 2 or 3 or 5, or you can increase it however much you want. It's just a parameter that people use to tune like networks. There's no more explanations on pooling layers and fully connected layers. It's mainly on the convolutional layers. And now we're back to code. These are all explained, so I'm going to look at the TensorFlow code on these convolutional layers. We have a familiar term, conv2D. 2D is an image 2D, but not when it's turned into a matrix, because in a matrix form it's 3D. We have filters, which correspond to these filters. And basically, this is an argument that you feed into this function to indicate how many features, how much features you want to extract from the image. So usually the more filters you have, the deeper the CNN goes, and the better it is. We have kernel size, which is how wide the kernel is. If we look at this one, the kernel is 3 by 3. The yellow square is 3 by 3. And I think usually the kernels are around that size too. Like it's pretty good. Stride, we talked about stride is how much the yellow square moves. One would be exactly this guy. You move right and left down by one step at a time. And then there's padding. Padding is what happens when you go towards the edges of the square. So in this one, it doesn't show the padding case, but for these edge pixels, sometimes you want to take like these 9, but it's already outside the image. So you pad it by a little bit more just to look at these edge pixels. That's what padding does. I'm not gonna introduce this in any detail. So basically vision transformers are not CNNs. And CNNs or vision transformers are basically another very popular model that people have been using a lot in order to process image and for like detection task and whatever, just because they throw transformers at everything. I'm not going to go into it at all, except mentioning that transformers are usually like NLP models, and they take in sequences, not images. And you might see already a big mismatch there, because when you look at images, they're 2D, and for sequences, they're more one-dimensional. It's like sequential. It's just a line of stuff. And in order to use transformers for vision tasks, they split basically like a square into smaller square, and they compress these squares and then feed it into the transformer model so that it's actually like a sequential task. That's all you need to know about Vision Transformer. And I'm talking about Vision Transformer because we have a demo on Vision Transformers, but you don't really have to know too much about Vision Transformer or how they actually work. So yeah, we can talk about code now, because coding is the most exciting part. Anthony, talk to me about this data set.
Right. So this data set was from Kaggle.com. If you're not familiar with Kaggle, we do have a Kaggle workshop on Thursday that I will be hosting in person.
It's in person. There's food.
And there's food, yes. So yeah, definitely need to. I mean, I need to go for the food, and because I'm hosting it. So basically, we have a data set with there's 70 types of dogs in it. Now that one, I don't know what type of dog that one is. I wish I did. Do you know what type of dog that is?
It's mostly Afghan, because it's still like
Yeah,
very
it's still
early.
early, right? Yeah, so it's an Afghan dog. Basically, this data set happens to be the case that like the first row is all the Afghan dogs, and like in the middle you have the Dobermans, and at the end you have Yorkies and all the ones that are out. It's like alphabetical. So yeah, generally that's gonna be the task, is to be given these pictures and figure out which folder here. You see the folder of all of the dog types. We're gonna try and see what type of dog that is. So that's a chow dog, yeah. So I love chow dogs.
Yes.
So yeah, I mean, I don't think there's that much more to say about it. One disclaimer, I guess, that you may be seeing here on the screen is there was a typo in one of the data sets. One of the data sets, sometimes they called it an American double space spaniel. So yeah, we replaced that. But yeah, just worth throwing that out there, because you might be wondering what's that. You don't have to worry too much about what's going on in that cell there. We're just kind of saying there's training data in this file that's in a dogs directory, right? So there's /dogs and then dogs.csv. That one actually gives the file paths and what that label is. So that's what we use to load the data. And I think that about covers the data set.
Yeah. So yeah, there's a file up here. It has the file paths, labels, and what data set it is. I don't think we ever covered data set, but basically there's usually three types of data sets. With the trained data set, then we have the validation data set, and we have the test data set. Usually the model only trains on the trained data set, and that's because it, okay, yeah, you train on a trained data set. And during training, you use the validation data set to determine whether the model is actually going in the right direction. So it still propagates using the loss given by the trained images, but in validation, they're computing these losses on metrics like accuracy using this validation set. It's not trained on it, but it's using these as a guidance to, oh, hey, your validation test accuracy is going down. So maybe that's not the right direction. So that guides the model on how it goes. There's the test data set, which is never used during training. And the test data set is basically just there just so you can test it later on whether the model is actually training on the right, it's actually trained right, basically. So yeah, I'm not gonna go over how we read these data sets. Basically, it's just file paths, and then for each file path, we're loading these images in. There's a very nifty function in TensorFlow Keras called tf.keras.utils.image dataset from directory. And that basically does all the work for you. All you need to do is tell them which directory these images are in. And these directories have to be separate into the folders of the classes. So in the Afghan folder, you should see all the Afghan docs. And yeah, you just tell him the folder path. And then the targeted image size and the batch size, and it'll give you the data set. And we do that for the validation set and the test set as well. We don't really have to look at the data. We know what these logs look like, Sharpies. Yeah, and then we go on to building the actual model. First of all, we do a rescaling here. And why do we divide the 255? That's because most RGB values are from 0 to 255s. But in a machine learning context, it's usually good to scale your data between 0 and 1s, just because it's more intuitive that way. It's like 1 is when a node is fully there, it's like on, and 0 is like off. So it's better to scale things between 0 and 1 rather than 0 to 255. So we divide everything by 255. And then of course we have the convolutional layers. We have the max pooling layers, convolution, blah, 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 blah. And then we flatten the max pooling layer. This is when we get onto the fully connected layers. This is when we get into the hidden layers. We have a 128 unit hidden layer here, and the final output layer where the output is the number of classes. Why do we have 32 and 3 as the params for convolutional 2D? Okay, yeah, let's go back to the documentation. What's this written? Okay, yeah. So filters, 32 would be the number of filters. So usually it's like either 32, 64, or 128. That's the default numbers. And usually as you go deeper into a CNN, you would have more filters just because that's the way it works. And the second number, the number 3 is the kernel size. Sometimes you can do like bracket 111 or like bracket 33, but for this case, we're only specifying a single number 3, which is kernel size of 3 by 3. And yeah, that's the size of the kernel. And that's already the model. That's very simple. That's how you build a model. And then in TensorFlow, we always compile the model just so it knows what you're dealing with, what loss function you want to use, and what metrics you want to use during training. The loss function, as we mentioned, is something that calculates how wrong the model is. In this case, we're using sparse categorical cross entropy, and this loss is usually used for multi-class classification problems. We mentioned binary cross entropy. That's usually used for binary classification. So like that would be for cats and dogs. But for this one, we have 70 classes, so we can't use binary anymore. We're using sparse categorical and cross entropy. And accuracy is it's pretty straightforward. It's just how accurate it is. For optimizers, Atom is just usually what it uses. Like I can't even explain it. It's like people usually always just use Atom, and in NLP they use Atom W. That's all you need to know. If you're struggling, if you don't know what you want to use, just use Atom. It's fast. Some people would say RMS prop, or what was the other one? But for the purposes of this tutorial, we're not telling you. Just use Atom.
There is just SGD, like
Oh yeah.
as the stochastic gradient descent, which is just gradient descent with just a batch size of 1, basically. It calculates it for each example in the training data set. But yeah, Atom, just use Atom. Atom's good. Atom's cool. He's a nice guy.
Yeah, cool. And then once we compile the model, we can just fit it. And fitting is basically training the model to teach it what to do, then nudge the values in the right direction. We feed in the train data set, the validation data set, and we tell them how many epochs we want to train it for. And usually it prints out this nice thing that loads while you're training. Since it's done training, I'm not going to rerun it again because I'm running Zoom and training at the same time. That would kill Zoom. But yeah, as you can see, as you go from epoch 1 to epoch 10, the accuracy improves because the model is doing its job. But if the accuracy is not improving, then you should check your model. Something's definitely wrong. The loss should be decreasing because that's how wrong your model is. So you want your model to be less wrong towards the end of training. And validation is the set that is not trained on, but it's just a reference value for you. So accuracy, you can see that it's increasing, so that's great. The loss, it's not increasing. It's not decreasing, which is concerning, but we can see that the accuracy is increasing. So whatever. Sometimes that happens, but the main thing that you're looking at is the accuracy, because that's your final goal. You want to see how accurate your model predicts, and that's basically it. Once you have the model fitted, you can use the model to predict things. So model that predicts, it will output something called YPRED. YPRED is just the predictions, and you can see here it's just a bunch of numbers, and we can check the shape of these numbers. It's 700 by 70. The first number is just batch size, and the second number is just the number of classes. And from here on, you might wonder, how do I get which class is right then? Because this is a big thing. How do we interpret this? We can look at the histogram of distribution of these numbers. They actually distribute across a wide spectrum. And I told you before, machine learning, we usually deal with zeros to ones. So this is not always great. So what a lot of people do is throw a softmax function at it. So we can look at it between 0 to 1. You can interpret it kind of like probability. So usually the lowest values here would be zeros, because would be very close to 0, because there's a almost zero probability that that's the right class, and the one with the highest probability would be the class that you want. And you can get that by just saying numby.archmax. What was that thing called? YPRED. That's not the right direction. There you go. And these are the class IDs of the predictions. And since there's 700 in that specific test batch, there's 700 different classes here. But if you look at the right image at the right index, then you would see which class it belongs to. And the archmax function tells you the argument that's has the maximum value across this axis. So yeah, it returns 700 length array. And you can see that if I did it wrong, then it'll do the max in the wrong direction and it'll give you 70 numbers that do not really represent anything. But yeah, very cool. But you can also see that the accuracy is actually really, really low. That's not very, very good. So you might wonder how can we improve this number? Because we can look at the train accuracy and that's like 70%. That's pretty good. I wouldn't say perfect. To increase that number, we can do something called image augmentation. And we do image augmentation because usually we are not given a very, very large data set. And in image processing, there can be like, when in image processing, there can be a lot of images with different like exposures or like brightness, but they're still the same thing. So like, I don't know, Airedale, if you increase the brightness by like a little bit, it's still an Airedale dog, but the model won't perceive it the same way. So you want to alter these images by a little bit so that when you feed it into the model, it's more robust that way, so that it's extracting the right features. So that it's not like extracting other features such as like, you can see that this dog always have like a very similar dark patch of hair. And if the model overfits, then it will just say, oh, if it has a dark patch in the image, then it's like an Airedale, but it's not always the case. Like this doesn't have a dark patch of hair. And when we do image augmentation, we make the model more robust to changes in the images. That's basically what we do. It's just a slightly different function when we import it from your directory. We have like the brightness range. We can rotate the image a little bit. We can shift the width a little bit. We can flip the image because flipping, it's basically the same thing. And we can shear it, which is just shearing the image. We can zoom into the image because it's still fundamentally the same thing. And you can do the same process again. You can see that I didn't fit it all the way. But in reality, you can still train it for probably like 20 or 30 more epochs, and it'll probably result in a better accuracy than before. Okay, it might not have the same train accuracy, but the validation accuracy would most likely improve in that case. And then Anthony is now going to talk about how to improve it even further with pre-trained models.
So yeah, that's a convolutional neural network, right? But we don't we want something a lot better. First of all, it'd be nice if we started from nothing. That model started with just the data that we gave it, right? But what we're going to do is now we're going to take a model that's been trained on like who knows how many dollars of compute and how many examples, how big of a data set it's been trained on. It's been trained on a lot of stuff and it's very, very powerful. And I'm going to share my screen now to talk about it. Are you guys seeing stuff? Or are you seeing a blue screen?
I can see it.
Oh, you can see it. Okay, great. Okay, so Hugging Face, first of all, just a quick plug. This website specifically is actually just a hub to share these huge models that companies like Facebook and Google publish. So one of the models is called a VIT model, Visual Transformer, like we talked about a little bit. It was published by Google. It's basically, if you're familiar with NLP, it's basically BERT for pictures. So we have like a model description. You can try it out on the website. It's very fun, very cool. So if you put in a teapot picture, it knew it was teapot, and you didn't need to give it training examples, kind of like how like we did with the dogs for the CNN. So we have they have a really nice API to train and fine tune their models. They call it fine tuning when you do more training on top of what's been done, basically. So we have basically, I might need to zoom in. Okay. So they also have data sets. That's kind of relevant because to work with to use their facilities and their code to train a model, you need to work with their data set type too, basically. So that's what I'll get into. NumPy, typical. This is to perform those similar transformations that I think they're the same transformations that the convolutional neural network went through. You can look at this you can Google this and you can look up like all the transformations you can do with this. It's a pretty nice library. And then transformers is the main Hugging Face one where you have the training arguments, which you pass to the trainer. And these are auto stuff that basically does stuff for you. I'm not going to go too in depth because we're running low on time. But generally, yeah. So they have a similar thing to that TensorFlow Keras thing where you just give it the directory, and it figures everything out for you. So it says it'll figure out the data set. It actually just canceled my runtime, so I have nothing loaded. So I'm just gonna have to explain it without any output right now. But yeah, anyway, for now. So it's basically the same thing that you saw with Keras, except this with the Hugging Face datasets library. You provide it the directory and it gives you 3 splits: train, validation, and test split. And then you also I save the model name because we're gonna use it a couple times. This is the name of the model that we were looking at right here. Everything good?
Yeah, sorry.
Okay. Cool. So now you can imagine like they have when they train these big models, they have specific ways that the model expects the data to be in, and that's kind of what's happening here. So Hugging Face has a nice feature called auto feature extractor, where if you give the model name to the feature extractor, it will it'll basically be able to pre-process the images in a way that the model will know what to do with it. This is the augmentations that we were talking about. This has nothing to do with this yet. But basically, we're going to put these two things together, and we're going to have a pre-processing function that's going to take all the images, and it's going to do all those augmentations, and it's going to prepare them to be used and train the model.
How do I know what inputs the model will take? Like what size the images?
What size?
Yeah.
Well, you can look at the model card first of all. So automatically, I see here that it was trained on ImageNet 21K, and the resolution's at 224 by 224. And I think you can assume it's RGB. So 224 by 224 by 3 is would be one way you can look at it.
Cool.
That's fair. Cool. So yeah, you can, generally Hugging Face, if you're using a Hugging Face model, you just you can look up pretty much anything you need on here. But they also link, I think usually they link like the actual archive paper, so you can click a link and read the machine learning paper if you're so inclined. But anyways, yeah, so we got the augmentations, and then we're gonna do all the pre-processing. So we're gonna use this function to apply it to each data set. So it's gonna get this gets all of the images for that split. So if you have like the training split, then it's gonna get all the images. And then this applies all the augmentations, and you just specify that it's RGB, and you convert it to a NumPy array to make it into an n-dimensional array for the model. And then you use the feature extractor to actually take that and put it into the form that it should be, which is 224 by 224 by 3. And then you assign it to the pixel values. So that's one of the important things. To use their models, you usually have to use the same names. So in the actual model over here, it expects that the pixels are called pixel values in the data set. So now they are. That's what this does. And then, yeah, just basically getting the train data set, validation, and test data set. The rest of this is actually really, really easy. Basically, I just get all the labels. So the trainer needs a couple things from you. It needs to know what the labels are, like what are the things it's supposed to be predicting. It needs to know how many of them are, and it needs to have mappings from like an ID to the label. So 0 becomes Afghan, and then like 70 becomes Yorkie or something. Yorkie is like the last one, I think. And then all you have to do is use their auto model for image classification. And this basically loads the pre-trained weights from the Hugging Face hub, and it gets the model name. You give it the number of labels, the stuff that I mentioned before. This is just because of the size of the data set. It's just some workaround that they put into their documentation. And then we make a training arguments thing where you say all of those, do you remember all those buzzwords that we mentioned earlier, like learning rate and stuff? That's where we put all this stuff in. So we have a number of epochs. I put 5 because I wanted it to be quick. Learning rate of a very small learning rate. This is a common one though. If you're never sure, if you're trying to do your own machine learning projects and you're not sure which learning rate to use, you can just use this or just Google like ones that other people use. The learning rate is usually like more of something that you do to make it even better, but it's not gonna like, if you're at like 0% accuracy, it's not gonna change your life probably. Maybe it will actually in that case if it's that bad. But anyways, yeah, so we have a few other parameters. I gotta rush through this. You can also push it directly to Hugging Face too if you fine tune it. That's a nice little feature. And then we load the accuracy or load a metric called accuracy. And then this is just the format for Hugging Face trainer models. It gets the argmax like you saw earlier, and it computes the accuracy. So basically, it takes the class that was predicted, and then it measures the accuracy. Was it the right class, right? Then we have the trainer object finally. All you have to do is say, you give it the model that we loaded from over here. We have this model, and we give it to the trainer, and we give it the training args from here. And then you specify the training and evaluation data sets and the metric to measure it. All right, that was a lot, but now we get to see the results, right? So we have this, wait, that's not the right one. Is that it? I thought I had more epics. What happened? Like, there we go. Sorry, I don't know what happened there. Okay, so here's the training results, and you can plot this. Usually this is something that like you might want to plot and visualize. But yeah, even just on one epic with zero dog training that we did before, well, like I guess one epic, but like not we didn't fully train it yet. It was already able to get 94% accuracy. That's because it was trained on a friggin' data set of like 14 million images. So that's the power of Hugging Face models. Already 94%. And after just two epics, it's already pretty much at what the final epic ended at. So these epics are probably not even necessary. You could have just left it there. But yeah, the validation loss is computed by the formula that you saw. It's the same sparse categorical entropy as the CNN. And yeah, it's same as the training loss. But like Alvin alluded to, you generally just care about the accuracy mostly, right? So yeah, it gets about 96% accurate on that. So yeah, that is Hugging Face models. If you guys are trying to impress anyone in an interview with a side project, I strongly recommend starting with a Hugging Face project. So some kind of image classification or an NLP task where you work with a model from Hugging Face. It's generally that's pretty like you're working with state-of-the-art models when you do that. So there's a lot of benefit. And last thing I wanted to mention is, like I said before, you usually need to use like GPU to train these. If you try to train this without a GPU, it will take literally like 24 hours. If you do it with it, it only takes like 1 hour. So it makes a huge difference. And if you are familiar with Google Colab, maybe you should have a Colab. I don't know if you have done a workshop on Colab, but yeah, so you can change the run type, the runtime type, sorry. So to specify GPU, and Google provides you a free GPU to train on. So otherwise I would not have waited 24 hours for this thing to fine tune. That would have taken forever. I just clicked GPU there, and Google provided me a GPU to work with. So yeah, I think that about covers it. I see there's 2 chats, forums, feedback form, cool. Is there any questions now before I stop sharing my screen? Anything you guys want me to go over about Hugging Face or about the model or about anything really? And this goes to Alvin too. If you have any questions for Alvin for what he covered with Keras and CNN, now would be time to say that.
These code would be shared later on. We will share the link to these code.
Yeah.
So don't worry about memorizing them. There's always tutorials online that shows you how to do it.
Yeah.
It's just an overview, like what a fit function does. Yeah. If no one has any questions, I sent a feedback form in the message in the chat channel. That's very important to fill it out. It's just so that we can get feedback on like whether it's like too difficult or not